In this video, we're going to look at how to analyze the position time data to look at velocity time and acceleration. We can see on the right-hand side, we have two plots that have formed. If you cannot see these, you can use this little line handle to move the separation of the data in chart so that you can see the graphs. So do that so that both graphs are visible. And one graph should be the position in the x direction in relation to time, and then the second should be the position in the y direction in relation to time. They should both be labeled as mass A to represent the point mass, the red dot that we set in the last video. As you can see, the change in the vertical distance or the rise between numbers in sequence is very small in comparison to the change in the run, which seems to be increasing as we go left to right. This trend shows up in both of these charts, as we can see that the top chart has a much steeper rate of change, whereas the bottom chart has a much lower rate of change. We can analyze these in regards to position time, and we can take this parabola or quadratic relationship and translate it to a linear relationship by applying linear regression. First thing we're going to want to do is actually change and look at just one dimension at a time by clicking on the y and changing it to the velocity in the x direction. We can now see that our position time graph, which is curved, results in a pretty much linear relationship between velocity and time, which we can now analyze and get the slope of by right-clicking on the graph and going to Analyze. When we want to fit a line to this data set, we hit Analyze, Curve Fitter Line, and it presents a line which can be auto-fitted down here in the bottom left. And that line is auto-fitted to our data, and we can see that we have the two parameters a and b, knowing that the equation is y equals mx plus b for a line. Our a, our first value, would be our m, our slope, and our second value b would be our y-intercept. These parameters here line up with the fit equation to the left. What this means is that when we take the analysis of velocity and time and we fit the line to it, we can find that the rate of change is a constant value, which is our slope, and that slope will be our acceleration. We can close that out. We can switch our dimensions from x to y and our velocity to vy. And we can see a similar relationship. We have a curve, and then we can see that this data represents somewhat of a line, and we can right-click on the graph and go Analyze, and we can move our data over. This one's a little hard to do sometimes. You have to sort of click on one of these data headers so you can see y velocity in the y direction and sort of shove it over. Now we can see our graph shows up here. We can set line, and we can auto fit a line, and we can see that our new slope is a number that is pretty close to 0, meaning that in the y dimension our velocity time graph is resulting in almost 0 acceleration, which is pretty good because we know that that rope, the wire, is holding the cart up against gravity. So there's a very small amount of vertical acceleration, most likely due to when I let go of the cart and it sort of moved up and down on the wire a little bit, or some other human error in the tracking software. So the acceleration here of our VT graph in the x dimension shows the acceleration left to right, which is a component of gravity's acceleration, and this almost non-existent slope on the y dimension is representative of our wire holding the cart back against gravity. Again, the a and b parameters down here are the slope and y-intercept of our y equals mx plus b equation. And if I want to get the a parameter for either line, all I need to do is drag the line of interest into the green spot, and the data will change down here at the bottom.